You know, we're swimming in a sea of numbers every single day. Stats, data, all sorts of measurements. But what are they really telling us? Well, it turns out there's a kind of hidden language baked into every number, a language designed to communicate one crucial thing: how much you can trust it. And today, we're going to learn how to speak it.
So let's just start with a question that I'm willing to bet has crossed your mind at some point. Aren't accurate and precise, well, aren't they basically the same thing? I mean, we use them interchangeably all the time in conversation. But in the world of measurement,
the difference is absolutely everything. And getting this right, it's the foundation for understanding how we can trust any number we ever see.
All right, let's break this down and get our definitions straight. What really is the difference between being accurate and being precise? Okay, so accuracy is all about hitting the target, how close you are to the true accepted value. It's about correctness. Precision, on the other hand, is all about consistency. See how those attempts are all bunched up together? That's precision. It doesn't even matter if you're hitting the bullseye, just that you're hitting the same spot over and over and over again. Let's make this even more real. Just imagine your GPS is trying to find a specific restaurant. That restaurant, that's our true value. That's our bullseye. So, look at this first case. The GPS pings are all over the place. That's what we call low precision. But, and this is the interesting part, if you were to average all those spots out, you'd land right on the restaurant's doorstep. So the system is accurate on the whole, just not very precise from one moment to the next. But now, check this out. In our second scenario, all the GPS readings are packed tightly together. That's amazing precision. The only problem? They're all precisely wrong. The cluster is miles away from the actual restaurant. So this system is highly precise but completely inaccurate. And you know, this can actually be even more dangerous than the first case because it gives you this false sense of confidence. This difference is so fundamental that scientists have developed a very specific language to talk about it. So let's move beyond the analogies and dive into the actual terminology they use. Here are the two key terms you really need to know. Discrepancy is basically the scientific word for accuracy. Just think of it as the discrepancy between your measurement and the truth. Easy enough, right? And uncertainty is the word for precision. It's a number that tells you the spread of your data, telling you how much uncertainty you have in your group of measurements. Now, a really powerful way to use this is to express that uncertainty as a percentage. It's great because it lets you compare the reliability of completely different kinds of measurements. So for example, let's say you buy a few bags of apples. You weigh them and find the average weight is 5.1 pounds, but your measurements have a spread, an uncertainty, of 0.3 pounds. The formula here shows us exactly how to calculate it. And that little triangle, that's just the Greek letter delta, which in science usually just means the change in or the range of something. So we just take our uncertainty, 0.3, we divide it by our average value, 5.1, and then multiply by 100 to make it a percent. We get about 6%. And just like that, we have one single number that communicates the reliability or the precision of our measurement. A lower percentage, of course, means higher precision. So how do we communicate this idea of precision every single time we write down a number, without having to calculate a percentage each time? Well, scientists came up with a pretty ingenious system for this called significant figures. Significant figures, or sig figs as you'll hear them called, are basically the digits in a number that are actually meaningful. Think of them as a built-in code that tells whoever's reading the number how precise your measuring tool was. A measurement from a high-tech digital caliper should look different from a measurement you took with a regular old ruler, even if they're measuring the exact same thing. Now the zeros are where things can get a little tricky. A zero that's sandwiched between other digits, like in 101, it always counts. A zero at the end of a number, after a decimal point, like in 1.20, also counts. That's a huge clue. It's telling you your measurement was precise all the way out to that exact spot. Zeros at the beginning, though, are just placeholders, so they don't count. The real problem is zeros at the end of a whole number, like 1300. Is that 2 sig figs? 3? 4? It's impossible to know. That's exactly why scientists use scientific notation. If you write 1.30 times 10 to the third, there's no doubt. You know for a fact there are 3 significant figures. Okay, so you've got your precise measurements. What happens when you actually need to do some math with them? Now this is critical. The rules actually change depending on what kind of math you're doing. There's one rule for multiplying and dividing, and a totally different one for adding and subtracting. When you multiply or divide, the rule is pretty simple. Your answer can only be as precise as your least precise measurement. Think of it like a chain. It's only as strong as its weakest link. So if you measure a circle's radius as 1.2 meters, that's 2 sig figs, and you calculate the area, your calculator is going to give you this long, messy number. But you can't report that. You have to round your final answer to just 2 significant figures, 4.5, because your original measurement limits your precision. Your calculation can't magically create precision that wasn't there to begin with. Now, for adding and subtracting, forget about counting sig figs altogether. Here, it's all about the decimal places. So imagine you're adding up these different weights. 2 of them are measured very precisely, but that middle one, 13.7, it only goes to the tenths place. That's your least precise measurement. That's your weakest link. So your final answer has to be rounded to that same spot. You have to round it to the tenths place, which gives you 15.2 kilograms. So at this point, you might be thinking, okay, that's a lot of rules, I get it, but why does this actually matter in the real world? And the answer is, it determines what we can confidently claim as being true.
So let's put this to the test with a real-world scenario. Imagine a track coach has a stopwatch, and it has a known uncertainty of plus or minus 0.05 seconds. 2 runners finish in a photo finish. The stopwatch reads 12.04 seconds for one runner and 12.07 for the other. That's a difference of just 0.03 of a second. So, the big question is, can the coach actually be sure who won?
And the answer, which might be surprising, is no, they can't. Just look at the numbers. The measured difference between the runners is 0.03 seconds. But the stopwatch itself has an uncertainty, a potential error of 0.05 seconds. Because the difference in their times is smaller than the uncertainty of the tool, we actually can't distinguish between the 2 times. It's within the margin of error. Scientifically speaking, it's a statistical tie. And this is so important. It's how we avoid making claims that our data simply can't support. It all really boils down to the single powerful idea, which is captured perfectly in this quote. The last digit written down in a measurement is the first digit with some uncertainty. Just think about that for a second. That last digit isn't a wild guess, it's an informed estimate. It's the boundary between what you know for sure and where a little bit of uncertainty begins to creep in.
So, the next time you see a number, whether it's in the news, in a scientific report, anywhere, don't just take it at face value. Remember this hidden language. Look for the story it's telling you about its own precision. Because the most important question you can ask isn't just, what is the number? It's, how much can I trust